Okay, great. So as I was saying, we're going to start with looking at what we had before. I had problems with this one here, and it wasn't a complete equation. The reduction potentials are the ones you need to compare to be able to put into the equation of, this will be the reduction potential for the cathode. So this is cathode, and this will be the anode, and then you subtract them. So to be able to see which one it is, you look at the smallest, the one with the smallest value, and if it, in this case, is negative 1.25, and that is going to be, rather than a reduction, like it's written here, reduction, and it's going this way, it's going to be an oxidation. So this is going to be a reduction, and this one is going to be the oxidation. And that means that the reaction is not happening the way that is indicated in the reduction, but it's going to happen on the opposite way. So let me go back to the equation, the overall equation, which is this one here. So when you look at the appendix, at the tables, there you're going to have reduction potentials. So this potential and this potential is the reduction potential, are the reduction potentials. Now, the one with the highest reduction is the one that is going to reduce. The one with the lowest reduction is the one that is going to oxidize. So oxidation, remember, happens at the cathode, and reduction happens at the anode. So what I'm trying to say before was that this reduction potential is the potential for the reduction, but in reality, this is the one that reduces, this is the one that oxidizes. So the reaction is happening backwards from the equation that you can find on the table. So this is the copper to copper 0. So this is going from +2 to 0. And that means that it's going, again, this is the axis. So it's 2 to 0 is going downwards. And if it's going downwards, that means it's a reduction. So this one at the anode is going to be an oxidation. And if it's an oxidation, this one is still a reduction. So the actual reaction happens going this way. Okay, and so we subtract. So another way of thinking about it is the way that is written here. And in this case, I've written this, again, the reduction, and I changed this to the oxidation. So I have written the equation the way that is going to happen in this chemical cell here. And then notice that I've changed the sign. In that case, then the E of the cell is going to be the reduction plus the oxidation. So if you study this again, you don't be surprised that you will get either this equation with a plus sign when this is the oxidation, or you'll get this equation with a minus sign when you use the reduction. So either way it works. As you can see, both of them will get to 1.104. So it just depends on how you view the oxidation. So here they're viewing it as an inversion of this, and therefore they are subtracting. So the minus sign is because they're using the reduction. So depends on the book, you might get this oxidation. It's the same thing. Okay, so again, these are both reductions. Let's look at what is being reduced and which element is being reduced and which element is being oxidized. That is important for you to figure out whether you're looking at an oxidation or a reduction. So in this case, you have oxygen. Again, the oxygen has a charge of 0, is neutral. And so 2x, two oxygens, 2x are equal to 0. And that means that x is equal to 0. That's the only value possible. So oxidation state in here, let me switch to a more permanent color. Let's leave it in red. It's going to be 0. And then I usually put a circle around it because these are not, I'm not talking about real charges. I'm talking just about what I call formal charges or oxidation states. Now, if I look at oxygen here, Again, oxygen is the more electronegative, so it's going to be negative. Hydrogen is positive then, and the overall is negative. So I'm going to say 1 oxygen plus 1 hydrogen is equal to -1. So what are the numbers for oxygen and hydrogen? So what are these values here and here? So I know that the more electronegative, the rule tells me that the more electronegative comes first, which means that I'm going to assign that one a value of, according to the periodic table, so that will be 1 and then -2 for the oxygen. So for the hydrogen, I'm going to say plus 1x is equal to -1, and then now I can solve for x. What is going to be the value of x? So this is going to be -2 plus whatever value is equal to -1. So -2 plus 1 is equal to -1. So x is equal to 1 when you solve this equation. So the oxidation state of hydrogen is +1. The oxidation state of oxygen is -2. So you can see that oxygen has changed oxidation states. Not all the oxygen, this oxygen here is still -2. If you do, this is +1. So this hydrogen is not changing oxidation state. This oxygen is not changing oxidation state. So some of the oxygens in this equation are changing oxidation states. Okay, so let me erase this messy thing. Unless you have a question. Okay, I'm going to try to leave the oxidation numbers there for you, so you can have some more time. You need to think about it. Okay, so let's look up now at this equation here. So I can see here zinc is neutral, so oxidation number 0. So I'm going to put a 0 here, surrounded by a circle, or encircled 0. And here I'm going to say this is -2, and therefore the zinc has to be +2, because again the charge is 0. There's no charge there. So zinc is going from +2. Let me switch pens. From +2. Oops, it was sloppy 2. +2 to 0, and that's being reduced. So this oxygen is going from 0 to -2 is being reduced, and this is going from +2 to 0, again, is going down, is being reduced. So these are the reduction potentials for the 2 half cells. Which one is going to be oxidized? The one with the lowest reduction potential. So if you look at these 2 numbers, the lowest is this one here. So this reaction then is going to happen on the other way. And since I'm using reduction potentials, then I have the reduction at the cathode minus the reduction potential of the oxidation at the anode. And so this minus sign is just to account for the fact that this reaction is going backwards than what is stated here. And then I get the value of the the voltage for that cell. Okay. So again, when you have the reduction equations, notice that the anode, the oxidation, the one with the lowest value, in this case, this one, is going to go backwards. And that's what this arrow is telling you. Okay, so it says calculate the standard potential for the reaction of this here, and using the standard potentials of the appendix, and this is appendix 6 in our textbook. Oh, yeah, it's there. Okay, so we looked them up, and we have the 2, and we can say that this reaction is spontaneous when the iodine is oxidized from, it's oxidized from iodide to iodine. Remember that this is going to be going backwards than what is indicated here, because that's a reduction. So it's going to be an oxidation. So again, we're going to calculate the E of the cell through this equation. We take the reduction potential at the cathode, and we subtract the reduction potential at the anode. and we can calculate the value. So that's what we are doing here. And I don't like this kind of equation because this is what is happening at the cathode. It's going to be a reduction, but at the anode, this is not the reaction that is happening. The reaction that is happening has the arrow going that way. So, and again, you can see that I used the minus sign. So that means I'm taking the reduction to these two numbers and subtracting them. So, okay, so if the book does that as well, then just be aware of that this, for the anode, the reaction is backwards. So again, we subtract the 2 and we get the voltage for the cell. So yeah, what they're saying on the next slide is going to be, this is a positive value. And it's going to be a positive value. Why? Because we always take the smallest and we say that one is going to go backwards. That one is the one that goes backwards. So we always will subtract the largest minus the smallest, and therefore we always get a positive value that way. So this is a voltaic cell. This is a battery. This is something that happens as spontaneous and produces electricity that can be used to run whatever you want to use electricity for. Okay, so let's look now at voltage and electrical work. So remember that the reaction that is spontaneous has a delta G that is less, delta G is going to be less than 0, and that's called free energy. It's called free energy because we can harvest that energy to be able to use that electric energy that is coming out from the reaction. So in order to get that energy out of the reaction, we need to separate it into 2 cells, a reduction cell and an oxidation cell, and then put a wire. And then we can run, let's say, our lamp or our motor in here. Okay, so when we have a cell, then we have a delta G that is going to be, if it's a voltaic cell, is going to be usable energy, and we can do work with it. And so how are we going to calculate the work? We're going to take the electrical charge times the E of the cell, and that will tell us how much work can be done. Okay, so I think I have a better slide than this. The electrical charge is going to be in coulombs, and coulombs are capital C. I have a better slide that's coming up. And so the potential of the cell produces what is called because it's electricity, motive force. So it's going to be able, we can use that force to do the work. And so the delta G that we can calculate for the cell can be related to the potential of the cell. So it's very easy to come and look at the table and look at this E of the cell. We're going to learn that this is a constant, and this is the number of electrons that are being transferred in the reaction. So we multiply those 3, we'll get the delta G for the cell. And if it's a voltaic cell, the one that we can use as a battery, that means that delta G is going to be negative. So this is positive always, this is positive, and this is positive. So we put a negative sign, which means that delta G is always going to be less than 0. Always, for a voltaic cell or for a battery. Okay, and let me just go to move forward. I'm trying to look at I spend a lot of time looking at this. Yes, so it's here. Let me introduce you to this because I think that's going to be easier. So this is a useful slide. I modified it from the original and put some more information in it. And so you might want to transfer this information to a piece of paper. During the test, you might want to have this in reference. So these are all the different kinds of units that we're going to use. So as we said, there's going to be an electron flow, and the electron flow that goes from one cell to the other on the outside wire is going to be measured in amperes. That means how much electricity is going through. So that is the charge per unit of second. Charge is expressed in the unit of Coulomb, and then coulombs per second will be the units of this current. And 1 coulomb per second, 1 coulomb per 1 second is called an ampere. And so that is, you take these two and put an equal sign, and that's telling you 1 ampere is 1 coulomb per 1 second. So what is that? So we can calculate, if we have an electron flow, we can calculate how much current is going through by taking the charge and dividing it by the time. So charge divided by time is equal to current. I'm not going to run out of space, but that's current. So we can also calculate the charge if we can measure the amps. And then amps you can measure with an instrument, which is an amperimeter. Those things that some people use to actually figure out what the voltage of the batteries are. I use that for my batteries to know when to throw them away. And so that meter, it's called a multimeter, can measure amps, and I can measure the time I use it, and therefore I can calculate what is the charge. So this is the same. It's just the equation has been solved for A in this case, or for C in this case. So they are under current. So that's how much current. Current is the flow of electrons which are carrying charge per unit of second. So that's the first one. The second is work. That means the useful energy. And that is calculated in unit of energies, which is joules. So the joules can be calculated by taking the charge in coulombs and multiply it by the voltage. So the charge times the voltage will give us the joules. And 1 joule is equal to 1 coulomb per 1 volt. Again, if you put an equal sign between these two expressions, you're going to get that expression that I just wrote. So because coulombs are related to this equation here, so we can take amperes per second and substitute them in here. So we can take this, which is 1 coulomb, put them in here, and we get to this equation here. Amperes times seconds times volts. So you multiply the 3, and you'll get the energies as well. Now, the other important concept is that of power. So power is how much energy is being used per second. So if you take the energy and divide it by the seconds, you have what is called the energy capacity. What is the capacity of the source of energy, in this case, maybe the voltaic cell, to produce how much energy can produce per unit of time. And that is called a watt. And so watt, it comes from the last name of a person, and the symbol is W. Again, a watt, 1 watt represents 1 joule per second. So joules per second. So again, this is an equality here. So 1 watt is 1 joule per second. And then the last one is, which is called the charges per mole, which is another ratio, what is the charge, which will be the coulombs per mole. And there is a constant, so it's called a Faraday. And that Faraday is equal to 96,500 coulombs per mole of electrons. So that means that if you get this ratio here in charge per mole, if you calculate the charge, you can actually also relate it to the moles per. So let me write in pen. So if you want to calculate the moles of electrons, is going to be equal to the charge times a Faraday. Is it right? No, excuse me. Let me check. Coulombs per mole. So this is Faraday's coulombs per mole. This is mole. So no, you have to divide it by. So divided by Faraday, by the Faraday constant, and then you can calculate how much charge is being produced. So the charge is going to be equal. Charge is going to be equal to Faraday times the number of moles, which is the same equation as this one. Is just solve for number. Here we're solving for number of moles. Here, so we're sending the Faraday to the other side, dividing. So this constant here, which is charge per mole, is going to allow us to transform a charge into number of moles, which is going to be important when we try to calculate the quantities that we need to have in a cell to be able to produce so much charge. Okay, so again, this is going to be something we can come back anytime, and please do print it. I uploaded a PDF, so you can just print this on a piece of paper. That's going to be useful, or copy it, or electronically, whatever you prefer. Okay. So I don't know where we were. We were here. Yep. Okay, so in this problem, they're asking us to calculate the delta G. Let me use the burning tool. So they're asking us to calculate the delta G and the work that can be done by this reaction. So this is a voltaic cell. That means it's producing electricity, and these are the voltage. So they have given us the voltage. So let me use a marker here. So they have given us the voltage. They have given, and they're asking us to calculate delta G. There is a relationship between delta G and energy of the cell. Delta G and energy of the cell are related to one another. And notice that this is the voltage of the cell. This is a constant, and this is a constant. N is the number of electrons being transferred. So we can calculate delta G from the E of the cell. These two are related by these two constants. So they're proportional to one another. Remember that it has to be a negative sign in front of it. It's minus NF E of the cell. So what do? We can say delta G. Oh, like that. This engine needs to go. Okay, go on. Okay, so the delta G then is going to be minus NF E of the cell. And we have the E of the cell. Now we need to, the Faraday constant is 96,500 coulombs per mole. And N is the number of moles of electrons. So if you look at this equation here, then we can see that magnesium is going from 0 to +2. That's 2 electrons. And copper is going from +2 to 0, again 2 electrons. So what is the value of N? N is equal to 2. So we need to have the balanced equation for the cell, which is in here. And then we need to count how many electrons there are being transferred. So in this case, 2. So we have N, we have F, and we have A of the cell. Now we can calculate the delta G. So the delta G is going to be equal to, oops, what happened? I disappeared. Let me erase it. Okay, delta G is equal minus 2 times 96,500 coulombs per mole. So the moles are going to cancel. This is 2 moles and this is Coulomb, so I'm not going to worry about it. This is going to be Faraday's, and then, excuse me, Coulombs, and then we're going to get the E of the voltage of the cell, which is 2.71. That's it. So once I operate on those, I'm going my calculator here. So 2 times 96,500 times 2.71 volts, I get 376,690. And this is going to be joules. So if you have used the right values, then just know that this is energy, and energy is expressed in joules, and that works itself out. So since this is such a big number, we can say then that delta G is going to be equal to 377. I'm going to round it off to 3 significant figures, kilojoules. Okay, let's see what they did. Yep, they have the Faraday's constant. They have the equation for the cell. They have the number of electrons. And that's all you need to be able to calculate. Oh, yeah, of course, they have the voltage as well. Why did I get 300? What did I do? 2 times 69. Oh, I put 69 rather than 96. Yeah, I confuse my numbers all the time. So yeah, so this is correct. So this is 96, and I put 69 when I did my calculation. So let me redo it again. 2 times 96,500 times 2.71. And that is 523. Oh, 523,030 joules. And that would be 523 kilojoules. Then I don't remember the number. Yep. Right. Oh, did I put minus? Nope, I forgot. So there we go. Questions? Do not confuse your numbers. I'm dyslexic, a bit dyslexic when it comes to numbers. And remembering numbers, I can never remember any number. Okay, great. So again, this is the E of the cell. The E of the cell is a voltaic cell, so it's producing energy, and therefore the delta G is going to be negative for all voltaic cells. Okay, next comes the standard hydrogen electrode, and that is kind of the reference, is called the reference electrode, or we can call the standard electrode, and that's because arbitrarily we have made that temperature to be, excuse me, that temperature, I'm thinking about temperature, that potential to be zero arbitrarily. So all the other reduction potentials that we are measuring are going to be based on how they relate to the water. So it's kind of like a zero button, it's like a tear button on the balance. Or in temperature is going to be, we decided that 273.16 Kelvin is going to be, which is the freezing point of water, in the centigrades is zero. So that's the arbitrary zero. We could have called something else zero, but we just went with water in the centigrade scale. So the same thing here, we're going with hydrogen as the standard or the 0 point. So the reduction potential for hydrogen is going to be exactly zero. And so this is a convention, we have decided is zero. And so this is the standard hydrogen electrode. And so the electrode can be constructed doing this way. My cat is going to come through. Okay, you can come through. No, my keyboard. Yeah. Okay. So, no, okay, so this can be constructed, and it consists of a hydrogen flow, a closed compartment, an electrode, so that there's electricity going by, so that you can connect this half cell to the whichever other half cell you want to connect it to. And so there's going to be hydrogen, and hydrogen is going to be transformed into protons, or protons into hydrogen. So this can happen both ways, and depends on what you couple it with. So this is the hydrogen electrode. So when you are measuring the standard potential, then you have a hydrogen half cell here and the zinc. So where you just connect them together, and you observe that the electrons are coming out of the zinc and going in here, and the hydrogen, the protons in the solution are going to be transformed into hydrogen. So this one forms hydrogen. So the hydrogen actually, in this case, is not flowing the way of the arrow, but is flowing out because it's being produced. So in this case, then it's going to be the energy of the cell is going to be the energy of the reduction. So the reduction is happening here. This is the cathode. And so how do we know? When the electrons come out, it's always the anode. So the other one will be the cathode, where the electrons go in. And so the electrons are going in here. So the hydrogen is the cathode. So that's the first one, minus the energy of the anode, where the oxidation comes. And the oxidation is going to be, these electrons that are coming out of here is because zinc ions are being transformed into zinc plus 2 ion, zinc metal, neutral zinc atoms are being transformed into zinc ions, and therefore shedding 2 electrons, and those 2 electrons actually travel down the wire. And the voltage is 0.76, that's the voltage for the cell. So the voltage for the cell is the reduction minus the oxidation of the zinc. And therefore you look at this equation, then we can calculate or find out what the reduction potential for the zinc is. And that comes to be minus 0.762. We can couple in this other one, we're coupling the hydrogen, and the hydrogen now is producing the electrons. So now the hydrogen is the oxidation, and this one is the reduction, because the electrons are going this way. So then the energy and the voltage is 0.342. So that's the voltage of the cell is equal to the reduction, which is copper plus 2 going into copper, because the electrons are coming this way. So there are electrons coming here. So the copper plus 2 electrons will form more of the copper. So the copper deposits in here on top of the electrode. Okay, so reduction minus oxidation. Oxidation is going to be the hydrogen, which is 0. That means that this voltage that we read here is going to be the voltage for the reduction potential of copper. So notice that here we have a positive value, here we have a negative value, depending on whether the reduction potential is higher or lower than that of hydrogen. And since hydrogen is 0, means that every time that the reduction potential for whatever you couple, you take a hydrogen and then you couple a second one, that second one will become negative if its reduction potential is going to be less than 0. So this is the case, and this is the case when the reaction potentials are higher than that of hydrogen, which is 0. Okay, so using this half cell with whichever other half cell you decide to use, then you're going to be able to measure the reduction potential for that other half cell. Okay, questions? Let me look at the time. Yep, so we can stop the recording momentarily.